Now, welcome back to the next episode of AP Calculus AB walkthrough, where last time we talked about introducing the idea of limit existence. But now let's talk about properties of limits that we can use to solve some questions. Now, on page 42, they introduced 6 specific rules that can be implemented into any of these formulas that we are looking to find the limit as x approaches a certain value. Primarily, starting with number 1, we'll recognize that if I'm looking for the limit as x approaches a of c times some function of x, c being a numeric coefficient value, we can just take it out and solve for limit of f of x as is. Now, the idea is that you further isolate for f of x, and you can just directly solve for the limit as x approaches a of that function f of x, worrying about multiplying the coefficient afterwards. The same can be said about number 2 here, where if we are given the limit as x approaches a of f of x plus or minus another function g of x, we can distribute this limit notation and look for the limit of each function f of x, g of x independently. Instead of looking for the limit of the combined sum or difference of two different functions, we can further isolate and distribute the limit notation to each f of x and g of x function that is being added or subtracted to each other. Now, you will guess that number 3 follows a similar philosophy. Again, instead of finding the limit as x approaches a of the product of two functions in terms of x, I can make my life easier. I can distribute the limit to both the f of x and g of x independently, look for the limits there, then multiply each of them. For number 4 follows very closely as to what number 3 was doing, where instead of dividing the two functions first, then finding the limit as x approaches a, I can distribute the limit notation to the numerator and the denominator separately, then divide the two values. Note that this is only possible when limit of g of x as x approaches a does not equal 0. Otherwise, anything divided by 0, as we know, is undefined. Now, the last two notations are still very similar to that of the previous 4 that we talked about. Starting with finding the limit of f of x to the power of n, I can find the limit of f of x first, then take it to the power of n instead of the former. Number 6, the same thing as the exponential one, but instead it is in radical form, where instead of taking the limit of the nth root of f of x, I find the limit of f of x first, then take it to the nth root. Okay? Now, all of this is important to know, but a bit of a warning here is that most teachers, especially in the Greater Vancouver area, will not ask you about solving limits in this manner. For example, in this limit question here, you'll be given something like limit as x approaches 2 of 2x cubed minus x squared plus 4 over root x plus 2. Now, if the question asks you to just evaluate the following limit, then you can take the action of just plugging in the value of 2 into where the x appears and see if you get a valid solution. So in this case, it would be 2 times 2 cubed minus 2 squared plus 4 over root 2 plus 2. Now, what does that make the numerator? Well, that makes it 16 minus 4 plus 4, and the denominator, root 4. Now, we should know enough math by now to get that this is equal to 16 over 2, which is 8. And this is a valid way to approach this question if, again, the question is only asking you, quote unquote, evaluate the following limit. The teachers and the classes that do question you on these types of questions will specifically use the wording use the properties of limits. Use the properties of limits. And that is referring to the 6 golden rules that have been laid in front of you. And only through these methods are you able to solve the answer and get full marks. Now, for a follow along of the example, we can take the following steps, where first of all, we know that this is a fraction, so how about we distribute the limit notation to the numerator and the denominator separately? So it becomes limit as x approaches 2 of 2x cubed minus x squared plus 4 over another limit as x approaches 2 of root x plus 2. Now, from here on out, we can do another cool thing. For the numerator, I can distribute the limit notation to each of the terms that are given in that trinomial. So it becomes limit as x approaches 2x cubed minus limit as x approaches 2 of x squared plus limit as x approaches 2 of 4. And that is all over square root of the limit as x approaches 2 of x plus 2. Now there's one more step I can take, and majority of this in the numerator comes down to a combination of rule number 1 and rule number 5. In other words, it would look something like 2, the coefficient being multiplied after the limit as x approaches 2 of x, close bracket, to the power of 3. Rule number 5, minus the open bracket limit as x approaches 2 of x to the power of 2 plus limit as x approaches 2 of just 4 again. And this is all being divided by now distributing it using the same rules of the numerator, rule number 2. I get that this is the root of limit as x approaches 2 of x plus limit as x approaches 2 of 2. Now the job is a bit more easier for me because given where I am with the limit notations, I'm asking you just limit as x approaches 2 of 2. Plugging that in, I will get an answer that's going to be 2 times, well, 2 to the power of 3 minus 2 squared plus. Now, the limit as x approaches 2 of 4 is just going to be 4 because the formula y equals 4 is independent of the value of x that we plug into it. Therefore, no matter what x is approaching, the value is always 4. Last but not least, this is all over square root of limit as x approaches 2, which is 2 again, plus the same philosophy, limit as x approaches 2 of 2 being just 2. Plug it in and you'll get somehow that you'll get 16 minus 4 plus 4 over root 4, aka 16 over 2, aka 8. So the task at hand is not so complicated. Your job is to apply limit as close as you can to the bare bone appearance of x itself. Do you have a coefficient multiplied to it? Great, take it out. Focus on taking the limit of the x to the power of 3. Oh, it's taken to the power of 3? Then let's take that power of 3 out and focus on taking the limit as x approaches 2 of just x. Okay? Now we can try solving one of these examples to see if you fully understand it, starting with example number 1, where limit as x approaches -1 of this sophisticated fraction. Note that they're asking you this question using the wording, use the properties of limits. Otherwise, I'm not doing all of this. Now, this means we can distribute the limit notation, limit as x approaches -1, to the numerator and denominator separately. And so I get something that looks like this. And I can go even further and distribute the limit notation to each of the terms that are being added or subtracted in the trinomial in the numerator and the binomial in the denominator. So it looks like limit as x approaches -1 of x to the power 4 minus limit as x approaches -1 of 5x squared plus limit as x approaches -1 of 1. Last but not least, this is all over limit as x approaches -1 of x plus the limit of 3 as x approaches -1. The last thing I can do to get even closer to the variable x with my limit notation is to be inside of the exponents. That would look like limit as x approaches -1 of x to the power of 4 minus 5, the coefficient going outside, on top of limit as x approaches -1 of x, close bracket, squared inside the exponent, like I mentioned, plus, well, limit as x approaches -1 of 1, that stays as is. And the denominator is, well, again, not that more complicated, so we'll also leave this as is. Now let's see if we can plug it in and get the values that we're looking for, starting with limit as x approaches -1 of x. Well, that's just -1 to the power of 4 minus 5 times, you guessed it, -1 squared, plus limit as x approaches -1 of 1, a function that is independent to that of the input of x, 1, and that is over -1 plus 3. Let's keep going and see how our math skills are. We'll get that it's 1 minus 5 times 1 plus 1 over 2, which is going to be -3 over 2. Got it? Now, as we proceed, there is going to be a new excerpt here that you need to recognize. And this is kind of the assumed aspect of what we've been doing so far, which is called the direct substitution property. Now, what we've been doing in getting as close as we can with the limit notation to just x is recognizing that x is both a polynomial function and or a rational function. But we could expand further. We could say that if f of x is a polynomial or a rational function, and the a that the limit notation wants the x to get close to is in the domain of f of x, then yes, we can directly plug a into all the x's in the function f of x, and we will get a tried and true answer of what that limit is. For example, in question number 1, I'm given the function f of x being x minus 1 times x plus 1. This is a polynomial function that happens to be factored already, and we'll recognize the domain is all real numbers. So 4, aka our a value in this limit, is going to be in the domain of f of x. Therefore, we can just directly plug in 4 into where x is and get that it's 4 minus 1 times 4 plus 1, which is 3 times 5, aka 15. Now, that's going to be pretty straightforward, especially with the rest of the examples here. But what if things go wrong?